Okay, this is going to be our third video on rotational motion. And so in the first two videos, we talked about a number of things. Specifically in the last video, so in the second video, we generalized our ideas about kinematics, and we generalized our equations that we originally developed for 1D kinematics in linear motion to now work for our rotational motion, right? So, and I've sort of kind of given a spoiler to this beforehand, but we might then ask, can we do this for other stuff? If we could generalize our kinematic equations to the rotational ideas, can we do that with other stuff? Could we do that to dynamics? Could we do that with energy and such? And yes, we're going to find that we can do that with everything, as I mentioned before. But so our focus for this video is going to be taking the ideas that we developed in dynamics, so in modules 3 and 4, where we talk about forces and we talk about friction and things like that, taking those ideas and expanding those and seeing if we can use them in this rotational context. Okay, and so let's start off. We're going to start off by looking at our sort of very widely used Newton's second law. So F equals ma. We have Newton's second law right here. And now we want to try to translate this into a useful equation that we can use to answer questions in this rotational context. Okay, so we know that we can rewrite our linear acceleration, our a, as r alpha, where r is our radius and alpha is our angular acceleration. And so if we do that, if we sub in a equals r alpha into Newton's second law, we end up with the equation that we see here. And so that's great, but it's oftentimes more useful to think about torques instead of thinking about forces when we're dealing with problems of rotation involving forces, right? And so maybe I should have boxed this off. Maybe I'm going to box Newton's second law here, and I'm also going to box this equation here, which I could have boxed. So this is just our definition of torque from last module. But so it's often useful to think in terms of torques instead of forces when we're dealing with these rotational problems. So let's, instead of writing down this Newton's second law in terms of a force being equal to a mass times a radius times an angular acceleration, let's incorporate this idea of torque. But let's start off by thinking of this as our torque being such that the force is always applied at 90 degrees to the radius of our lever arm, or whatever it is that we're applying this torque to. Okay, so always at 90 degrees to our r. So basically we end up with our theta of 90 when we're thinking about things in these terms. And so our definition of torque simplifies down to this equation here. And if we then replace this f here with the f we've just defined above in number 2, we can write down the equation that we see here in number 3. Okay, and so we're going to find this is very useful, except I'm going to make one more sort of abbreviation that's often made. So we're going to write tau, like our torque, is equal to I times alpha, which is our angular acceleration, where I've simply taken these variables here, m r squared, and turned them into I, where I is what's called our moment of inertia. So the moment of inertia is going to be a quantity that's defined for an object and whatever point it is that we're trying to rotate it about, right? And we're going to see, I think I've put it in here. Yeah, we're going to see a number of these sort of in a moment. But let's start off just by remembering. Well, I've boxed it off here. This equation tau equals I alpha. So torque equals moment of inertia times angular acceleration, where I is our mass times radius squared, is going to be the sort of central equation we're going to want to use to solve problems in dynamics when we're dealing with rotation. Okay, so definitely keep that one in your mind, and we're going to sort of make use of that. I think we have an example coming up, so we'll make use of it there. Okay, so we started off here, sort of building this equation, this equation that gives us torque in terms of our moment of inertia and our angular acceleration. But we want to realize that whenever we're talking about these masses in these moments of inertia, we're talking about point masses, right? So whenever in the past we've talked about masses, or usually when we've talked about masses, we're thinking about a point-like object, but we can't really do that for macroscopic objects that have extent in a number of different directions, right? Like things in the real world, like cars and balls and falling bricks and things like that, have width, height, depth, right? They have extent, and so their mass is distributed over this volume, right? And so it becomes very important here when we're talking about these objects rotating, what sort of axis they're rotating about and how this mass is distributed around the axis, right? And so I really ends up being this sort of sum of all the point-like masses that make up this object times the radius squared that point-like mass is from the this axis of rotation, right? And so I've written it out here, but this is not a very useful form of it, because unless you're dealing with some finite number of point-like masses, which really doesn't have an analogy in the real world, it's just sort of a sort of way to make our problems simpler when we're doing these examples, or maybe you could sometimes in the real world approximate a system as being made up of point masses, but generally speaking, if we're dealing with large objects that have extent, we need to employ integral calculus to calculate the I values of a number of these objects. So doing these integrals and using calculus here is beyond the scope of what we're doing in this course. But if we're given these I values, like we don't have to use the calculus to calculate these I values, but if we're given the I values, we can then use these I values to answer some interesting questions about a number of different problems, right? So what I have here, this table that you guys see here with a bunch of different shapes and their axis of rotation, is a table that came from the textbook, right? And so you can see here what you have is the object. So let's say this first example here, we have this hoop, and it's being rotated about the cylindrical axis, right? So the cylinder axis that runs through the center of the hoop, right? I mean, that's not the only axis that we could rotate this thing about. We could rotate it about a number of different axes, and we have an example here where we have the hoop that's being rotated where the axis is sort of cutting across a diameter, right? And really, in principle, you could rotate this around any axis you wanted. You could draw, any axis and rotate it however you wanted. The axis wouldn't even really need to be in the object. You could have an axis that was way outside of the object and still have to calculate that. But somebody's gone to the trouble here of calculating using calculus, doing the integrals here, calculating all of these I values for us, so we can use these I values in solving some problems. So if you end up having let's say a solid cylinder or disc like this, and you're rotating it about its about the axis that runs up the sort of center of the disc here in this direction, then you just come to this table and you look up the I value and you say, oh, well, its moment of inertia, since it's rotating about that axis and it's a solid cylinder, is mr squared over 2, right? Where m here is the mass of the object, r is what's shown on the diagram as the radius, and so you just have to find those two values. You plug it in here, and right away you have your moment of inertia. Then once we have that moment of inertia, we no longer need to use calculus for anything. We can then simply plug it into the equations that we have here. We have our I, and then if we had alpha or tau, we could work backward, or if we were given an F and we had R and alpha or whatever, we could then work with that I value and find out things about the system, right? So So remember this table here, it is in the text, it is here, and generally if I'm going to give you a problem, either on an assignment or on a test, well, maybe on an assignment I'd have you look it up in the table here, but on a test I would probably give you the I value, or it would be something that you could very easily find. And then once you had that I value, you could proceed with answering the problem. Okay. And so let's do one example here. Again, we're only going to have time to look at one example because this chapter spans so much material. But even though we're only looking at this one example, you can imagine that all the examples we did in sections or in modules 3 and 4, where we were dealing with forces and friction and such, almost all of those would have sort of rotational parallels that I could make problems out of, right? We could have systems set up where we would end up with these rotational problems that basically we can attack using these ideas we've just developed here. So even though we're only looking at one of them, there's a whole rich collection of problems we could see. There are a number in the textbook that you guys can look at. I encourage you to do that because there's almost certainly going to be problems like this on the final, right? So here, as I said, we're looking at one example. The example we're looking at is 10.7 from the textbook. It's a mass distribution on a merry-go-round. Okay, so what are we doing here? We're basically looking at somebody pushing a merry-go-round, like a playground merry-go-round around. So let's read the problem. Consider someone pushing a playground merry-go-round with a force of F equals 250 newtons exerted at the edge of the merry-go-round perpendicular to its radius. The merry-go-round has a mass of m equals 50 kilograms and a radius of 1.5 meters. Assume the merry-go-round is a uniform disk with negligible friction, and we want to calculate the angular acceleration when in part A no one is on the merry-go-round, and in part B when an 18 kilogram child sits 1.25 meters from the center of the merry-go-round, and we're going to consider the child to be a point mass in this case, which is good because then we don't have to worry about rotating this child with some extent around a radius that is not sort of going through that object, right? So let me maybe start off just by drawing the problem here in case anybody's having trouble visualizing it. So this is our top-down view of the merry-go-round, right? We have some merry-go-round. This is the center of the merry-go-round. It's going to have this will be the positive direction of our angular velocity. This is our radius here, and somebody's applying a force directly perpendicular to that radius. This is our F, okay? And so maybe I'll try to remember to talk about what if this F wasn't exactly perpendicular to this merry-go-round. Like how would we approach a problem like that? But for now, let's take a look at this force being perpendicular to it, and well, let's get started here. Okay, so what do we want to find? We want to find angular acceleration with nobody on the merry-go-round, right? So the merry-go-round has a mass. That's the mass m, and we have our radius up there. Okay, so all of these are defined. Well, I guess we don't have our angular acceleration, and we don't have this angular velocity, but we will find the acceleration. We could obviously then get angular velocity or whatever, right? So let's start off from our equation. We know that tau equals I alpha, and with nobody on this merry-go-round, we can very well sort of approximate this merry-go-round as a, well, I mean, the problem tells us we can approximate this as a uniform disk, right? So we would go to our table. We would look for a solid cylinder or disk, right? We have our solid cylinder or disk right here, right? And so we can see that, and again, we see that our axis of rotation is cutting through the disk. So imagine that this was a very small disk. We could imagine that that it look like this, right? Maybe that's not a great drawing, but you can imagine that it looks like this with our axis of rotation cutting through it. And then you can just imagine that we flip it up like our merry-go-round. And so we have our axis of rotation like that, right? This thing is spinning like that. So this is for sure the equation that we want to use for our moment of inertia. Let's now apply that. So we know that with no additional weight added to this, or no additional mass sitting on the merry-go-round, which we will add in part B, we know that I is equal to I have the numbers here, I think, but we'll actually go through the calculation of it. So it's 1/2 mr squared, and so that's just equal to 1/2. Well, we're told m, the m of the merry-go-round, that's just our capital M here, and so that's going to be 50. And r squared, well, we're told that the radius is 1.5 meters. We need to square that. If you run that through a calculator, you will find that our I is 56.25. And I didn't mention this before, but the SI units of of our moment of inertia are going to be kilogram meter squared. Kilogram meter squared. Okay, so that is, I mean, you can see that right away from this, right? Our mass comes in at kilograms, our radius comes in meters, but then it's squared, so it's going to be meters squared kilograms, right? And so those are the SI units for it, and this is the value that our merry-go-round has with nobody riding on the merry-go-round, right? Also, we want to think about what tau is, right? Like we have I, we can also get tau. Tau is also equal to, from our work in the last module, we remember, tau is equal to this value here, but as we're told that the force is being applied at 90 degrees to our radius, we know that that the sine of 90 degrees is just going to go to a 1, and this is going to be Fr, okay? And so we're also told what F and R are. We know that F is 250 newtons, and R is 1.5 meters. If we do that calculation, we're going to find a tau value of 375 Newton meters, right? And so that's our tau value. Maybe I should have made these dotted boxes, but whatever. And so we're kind of almost there, right? We have the tau. That's not going to change in either part A or part B. That's always going to be the tau. Our moment of inertia will change in part B, but for part A, we have our I of 56.25 kilogram meters squared, and so here we can simply solve, right? Let's take this equation here and solve it for alpha. So let's slide the I over. We're going to end up with alpha equals tau over I, and now we just plug in numbers. So we're going to end up with 56.25 over oops, I flipped those. This should be our tau. So this is going to be 375, and this is going to be 56.25. And if we do that division, I have the numbers here, I think. Yes, we're going to end up with an alpha equal to, and this is for part A, we're going to end up with an alpha equal to 6.67 radians per second squared, right? And so that is our angular acceleration that we were looking for part A. Now in part B, what happens? We have a child that moves on to, and maybe I'll draw it again here. So we have part B. We're going to have the same setup. Oh, I can try this fancy circle tool. Let's see if that works. We're going to have this circle. Yeah, it works. Okay, so we're going to have this merry-go-round. It's going to have a center here. It's going to have a radius here. And let me relabel this. So we're going to have R, we're going to have M, we're going to have our force being applied here. Everything's the same, except that now we have a child sitting here at 1.25 meters. sitting at the edge, not quite at the edge, but close to the edge of this thing. Let's label their mass capital M. And what are we told? We're told that they have a mass of 18 kilograms. Okay. And so now we need to also consider the moment of inertia supplied by or added to our total moment of inertia by this child, right? So we need to think about, okay, well, I total, I'm going to call it I total, is going to be equal to the I that we just calculated, which is the moment of inertia of the merry-go-round itself. But now there's also going to be a child sitting on this merry-go-round, right? So there's going to be some I from the child. But what is I from the child? Well, we know that the definition of our moment of inertia for a point mass is simply, where do we have it? Up here, mr squared, right? And so if we approximate this child as mr squared, then we can very easily calculate sort of what that moment of inertia from the child, or sort of contributed by the child, is going to be, right? So we can do that right now. We know that the mass of the child here, I guess I could have rewritten this as like I can call this big R, and then this is going to end up being mr squared, which is going to be equal to 18 times 1.25 squared. And if we do that calculation, we're going to find that IC, where do I have that? Somewhere. IC is 28.13 kilogram meter squared. Okay, and so because we have the initial I from up here in part A, we can simply now substitute in here that we have 56.25 from the merry-go-round itself, plus the new 28.13 from the child, and I'm kind of making a mess of it here, but let's rewrite it down here. That our new I total is going to be, I have it here, 84.38 kilogram meter squared. Okay, and so this is now the new moment of inertia for the system with a child sitting on the merry-go-round. So the whole system together now, right? And now we simply have to go back to what we did before. The torque, well, the force applied by the person pushing on the merry-go-round hasn't changed, and so the torque hasn't changed. The only thing that has changed is our moment of inertia, right? So we can go right back. Let me scroll down here a little bit. We can go right back to the equation that we had just above here. So alpha equals tau over I, right? And we can simply substitute in for these values, right? Our tau hasn't changed. This is still 375 Newton meters, and our I has changed. So this is now going to be our new value of 84.38 kilogram meters squared. And so I wouldn't normally include the units here in this intermediate step, but I did this time, so we'll go with that. And what do we find in the end? We find that alpha is equal to 4.44 radians per second squared. Okay, and that's the answer for part B. Let me just very quickly, or no, we can actually, okay, so let's talk about a few other situations here. So this kind of ends this example, and this is where I was sort of originally intending on cutting off the video, but I'll just make a few more quick notes here, because there's really a sort of rich collection of problems that we could build out of this, like even just with this one single example. What if instead we didn't have the force being applied at 90 degrees to our radius, but if instead we had the force being applied at some other angle? Here, maybe I'll add a page to this just really quickly. which I may just cut out later for the actual notes. But imagine we had our radius here, and then instead of applying the force like this, let's say we applied the force at some angle like this, right? So we can imagine that this would have been the 90 degrees, and we have some angle theta in here. How would we approach this problem? Well, we would need to, I mean, basically we're getting back to this idea of what is a torque when a force is applied at some angle, right? So we have our torque defined like this, but then we made that simplification where this just went to 1 because the angle was 90 degrees. Now the angle is no longer 90 degrees, it's 90 minus this theta, right? Like this would have been 90 degrees, and now we're turning it back up some theta number of degrees. So somewhat less of the force is going to be going into torque here, and some of it's going to be going into actually pushing this object sort of on the side. And we may get into more problems like this sort of later, where we have rotating bodies and stuff like that. But we can think about it right now. Sort of how would we approach this problem if we were given this problem right now? Well, really, all we would need to do is get the part of the force that is pushing 90 degrees to the edge of this, or tangent to the edge of our merry-go-round, right? So we would simply break this force vector up into its two components here. We'd have some part of it that would be going this way, some part of it that would be going that way. We would solve for this part here that was actually the force that's fully perpendicular to our radius. Once we had that force, we could then just substitute it in and do all the work that we did up here using F perpendicular instead of just plain F, right? And then we could work back and find out what F was, right? Another question would be what if we didn't have the child sitting on the merry-go-round here, but we threw some sort of other object on top of the merry-go-round, right? Like let's say we had the merry-go-round like this, and we know that this gives us our I value. We wrote it down just up here, right? We said, where did I write it? Up here, that it's 1/2 mr squared, right? So we know that this is 1/2 mr squared. But what if, instead of putting a child on there, we took, I don't know, a big rectangular board, and we threw it on there like this, right? And now we wanted to rotate this thing about that common axis that cuts through the board and the merry-go-round, right? How would we tackle that? Well, we would need the I total again, right? So we need to find whatever I total is again, and in this case, it would be the I of our merry-go-round plus the I of this rectangular object. And I'm kind of getting a little creative here with the notation, but you can use whatever notation you'd want. Maybe more convenient to go something like this: I1 and I2, where we already know that I1 is going to be the moment of inertia contributed by our merry-go-round itself, and I2 is going to be from this board. Well, if we knew the length and the width of the board and we knew its mass, we could come up here and we could say, oh, well, this is basically just a slab through an angle perpendicular to it. We can easily, if we know the length and the width, we know what A and B are, where we would know what the mass of it are, and it would just be m times a squared plus b squared over 12, right? So we would end up with an I here that was 1/12 m a squared plus b squared, right? And so we could then, and again, this mass would be different from this mass. Maybe I'm kind of killing the notation here, but you can see that if this was the mass of this object and this was the mass of our merry-go-round, we could then generate an I total and figure that out, right? And so you can imagine any number of different sort of permutations of this problem that we could do. We wouldn't have to have a merry-go-round. We could be applying the force at the edge of this thing. We could be doing all kinds of things, right? But basically, you can see sort of from this one example how you can generate a whole class of problems that we can now tackle using these tools, right? And so that's really all I'm going to say about this, and we'll move on to a new topic in the next video. But definitely take a second to either look at these problems in the text, or you can cook up your own, really, and just see sort of what they look like as you play with them. Okay, I'll see you guys in the next one.